This is the second part of substitution reaction. So this chapter, as I said, is really huge. So I've divided the chapter into about 6 or 7 presentations. All right, so this is the second one. And we're going to go ahead and get introduced to SN2 and SN1 reactions. All right, so let's look at the nucleophilic substitution reaction first, just the generic stuff, right? Just general stuff. So when we say nucleophilic, it means we have something that is negatively charged. Substitution means that you are substituting one thing for another. Okay, reaction of course, a reaction. All right, and so let's look at the different parts that we have for a nucleophilic reaction. So here you have a substrate. I've kind of color coded it a little bit so it helps you to understand all the moving parts for the reaction. So we have a substrate here, and the substrate is an alkyl halide. Then we have a nucleophile, which is negatively charged. And then we have a product, which now has the nucleophile on it, and then the leaving group, okay, over here. So here the leaving group was blue, and that's what I made it over here as well. So you can see that that's the leaving group. Now, what's going on here is that the nucleophile is attacking the substrate in some way or reacting with it and then displacing the leaving group. So the leaving group is gone now. Okay, so let me just go over some things again here with you. Substrate, nucleophile, product, and then leaving group. Look at the nucleophile, look at the leaving group. Both of them are negative, correct? Now, one of them could be neutral also, all right? But that's something we have to talk about as we go on. Here I've given you the shorthand for all of these, and you feel free to use these. Don't use your own. If you are, then you have to give me a key for it. So substrate, nucleophile, product, and then a leaving group. Now, do you call this one here X as a leaving group? You can label this as a leaving group also, but for right now, I will suggest you look at the right-hand side, the product side for the leaving group, okay? Although the substrate has the leaving group on it. The main idea of looking at a leaving group on the right hand side is so you know whether it's a neutral one or it is charged, okay, because it's not going to be positive, okay, that's for sure. So it's either going to be negative or neutral, but I need you to understand what a leaving group is, okay? So look for it on the right hand side. You look for it on the left also on the substrate because the substrate has the leaving group. All right, so let me just say you have double work to do, okay? You have to look for it on both sides. Okay, so here are some examples. Okay, so here's the nucleophile, here is a substrate, and then on the right hand side I've given you the product and of course the leaving group as well. So again, I've color coded these things for you so you can see them clearly what's going on. So when we talk about these kind of reactions, you know, the main questions that arise is what's really going on here. Okay, so by that I mean, is this bond breaking first and then the nucleophile is attaching to the substrate, or is the substrate being, you know, reacted by the nucleophile at the same time as the X is still there? When is the X leaving, right? When is the leaving group leaving? That's the bigger question here. And when is the nucleophile attacking the substrate? That's another one. Now, or the same one, however you want to look at it. Then the other thing is nucleophile is negative and then the leaving group is negative. Why is it that the nucleophile can get rid of the leaving group? Why is the substitution even taking place, right? Why is this reaction happening? So I'd mentioned to you before about acid-bases reaction that you're going to have to predict whether an acid-base reaction can occur or not. It's the same thing here. You're going to have to predict whether these reactions can occur or not, because just because you have a negative nucleophile doesn't mean you're going to have a reaction. Those are the things we're going to study here. This here, I just gave you a little bit of a review for the kinetics of chemical reactions. So if you remember, zero order, first order, second order reactions, and they all depend on how the concentration of the reactants will affect the rate of reaction, not the concentration of the product, but reactant. So zero order is when the rate of reaction is unaffected by the concentration of the reactants. First order is when you double the concentration of reactant, then the rate also doubles. And here, if you double the concentration, then the rate is quadrupled. So it depends, not everything is going to affect the rate of reaction, not everything, meaning not every substrate or not every reactant is going to affect the rate of reaction. So you have to do the study experimentally. So you take your reaction and you take it into the lab, and then you change the concentration of one, keep the other constant, and then you do this experimentally to figure out. Okay, so there's no other way to do it. You can't predict any of these things. Okay, and then we talked about the theories for kinetics, the transition theory and the collision theory. I'm not mentioning the collision theory here that much because we're going to be talking a lot more about the transition theory, okay, which has a transition state, which means that you need that amount of activation energy in order to get to the transition state, which is a high energy state. Okay, so once you cross that, once you have that much energy, then your product is kind of a guarantee. All right, and so the nature of the transition state will tell you what kind of product you're going to get. The nature of the transition state tells you also what kind of reactants are involved in that transition state. So it's a really important part of chemical reactions. So here is an SN2 reaction. Now this slide is just to introduce you to a couple things, and then we'll move on from here. Nothing much going on. We write the SN2 reaction like this, so please note that. Chemists are very picky about how they write things, so it's not going to be this, it's not going to be this, it's actually this, right? So you see that. Now I don't really take off points if you mess up a little bit here and there, but I will encourage you to write it like this, okay, as much as possible. The more you have a better writing, the more you understand things, the clearer you are about the concepts in there. Okay, so here S stands for substitution, N is for nucleophilic, and then 2 means it's a second order reaction. Okay, so bimolecular, meaning that's a second order reaction. So that's what all of this means. So let's go ahead. Here is an SN2 reaction example. Okay, and so here is CH3Cl, which is methyl chloride or chloromethane, treated with hydroxide, giving you an alcohol as a product, and then chloride is the leaving group. Okay, so what do? We go into the lab, we do the experimentation, we try to keep the one of the reactants, which is the substrate, constant. So here the substrate is constant here, and here experiment number 1 and 3, and you can see that if it's constant here, you can now change the concentration of hydroxide, which is the nucleophile, and see if the reaction rate is affected, and you can see that it doubles. Okay, so if it doubles, when you double hydroxide, it means it is first order according to that. Then you can keep the hydroxide constant, okay, which is right here, and then change the concentration of the methyl chloride. So here it is doubled, and then look what happened to the rate also, it doubled. Okay, so if you're doubling the substrate concentration, the rate is doubling. If you're doubling the concentration of the hydroxide, the nucleophile, the rate is also doubled, which means that this is the rate equation, which is rate is equal to K and then methyl chloride and then hydroxide, which means both of these things are needed for the transition state. Okay, that's what it means. Also, it means it's first order with respect to methyl chloride, first order with respect to hydroxide. Okay, so which means that the reaction is bimolecular. Bimolecular meaning both of these are required for the reaction to happen, which means that they are both involved in the transition state, as I said. So you have to do this experimentation in order for us to be able to predict that this is a second order reaction, right? So first order, so 1 plus 1 is equal to 2 because both of these, and since it's not written, it's understood that it's 1 and 1, so 1 plus 1 is equal to 2, so that's what makes it a second order reaction. Okay, so that's how this SN2 is working. So once we know it's a second order reaction, now we can try to predict a little bit of the mechanism for this reaction. So here is the substrate, okay? And remember what this second order means. It means that the transition state involves both the substrate and the nucleophile. That is the whole point of the second order reaction, okay? So here is your substrate. Here is the nucleophile. The nucleophile is attacking the carbon center, which is the substrate, and then you end up getting this kind of an intermediate, which kind of looks weird because you have 5 bonds on carbon, but see what's happening here is that this bond is forming and this bond is breaking. So both of these bonds, you can't really tell which is forming and breaking, right? But you know the leaving group is going to go away. So these bonds are forming and breaking, and then eventually the BR goes away. Okay, so I mean, there is still so much to talk about, as in, why the bromine is leaving, right? The bromide, why is it leaving? We still have to talk about that, but I'm going to mention a few things over here regarding this part here about the electrophile. Okay, so remember, when you have a nucleophilic attack, so if this is the nucleophile, you have to have an electrophile. Okay, so this is the nucleophile, which is the hydroxide, and the electrophile is the positive center. Okay, so this carbon is the positive center. How is it positive? Because bromide here, or bromine here, is more electronegative, and it's just slightly more electronegative, but that's enough for it to cause a charge distribution. So this carbon becomes a little bit of delta positive. All right, and so that's the electrophile. That is why you don't see the attack anywhere else on the substrate. You see it only on the carbon that has the leaving group, okay, because that is the electrophilic carbon. So first of all, you have to understand, and that's why we need to know where the leaving group is, because wherever the leaving group is, that bond is the polar one. That's the one that's going to be the electrophilic carbon, number one, okay, about the substrate. Now, for the second part, it attacks from the back side. The nucleophile is attacking from the back side of the substrate. So why is it attacking from the back side? Well, the front is already occupied, right, over here. Remember, carbons are tetrahedrals, so it's like an umbrella. All right, so if you have an umbrella and if you're holding the umbrella, well, you already are holding the umbrella. That space is already occupied, so which means the back side is the one that's available. Okay, that's the open space. That's the one that is sterically less hindered. There is no crowdedness there. Whatever word you want to use, okay, I would suggest you start using the word steric hindrance. So there is lack of steric hindrance or no steric hindrance at the back over here. So again, think of it as an umbrella. And then so there's open space at the back. That's where the attack occurs. Okay, so it's going to be a backside attack. So once that happens, now you can see the bond forming and the bond breaking, okay, from either side. And then I want you to note the last thing that is happening here, okay, and that is that the tetrahedral has inverted. So look at the starting material and then look at the product. Okay, so if you look at both of them, you can see that when the nucleophile attacks from the back side, it flips the umbrella to the other side. Okay, right now the umbrella is facing this side, now it's facing on the other side. So if you started with R, you end up getting S. If you started with S, you end up getting R. So there is inversion of stereochemistry. Okay, that's going on. So there's lots going on in this, a very simple reaction. And right now it seems a lot because it's the first time, but eventually once you get used to it, you understand. Okay, so here is the substrate. Here is the nucleophile with the backside attack. Then you have the transition state. Remember, this is the transition state symbol. So you have a transition state where the bond is breaking and the bond is forming. One other thing I want to mention about the transition state is that it's given in square brackets. Okay, so you know that it is a transition state. And then finally, you have the product in which you have inversion of stereochemistry and the leaving group is gone now. Okay, and you have a new bond formed between the carbon and the nucleophile. So lots going on in this one simple reaction. And the last thing I will mention before I move on is that this was a second order reaction, and that's why the nucleophile and the leaving group, or I should say the nucleophile and the substrate, are both involved in the transition state. Okay, because it is a second order reaction. Here is the energy diagram of such a reaction. So, I mean, this, I don't know, I'm not going to spend too much time here, but, you have seen this before. So here is the products, here are the reactants, here is the activation energy you need, and here is the transition state, right? So where the nucleophile is attacking the substrate and the leaving group is going. So you have dash lines, which means formation and breaking happening. And then, of course, you end up getting the products where the leaving group is gone, okay? And so this reaction happens to be exothermic reaction because the products have lower energy. You should be able to draw these kind of diagrams out. So SN2 stereochemistry, I just want to mention it again that there is an inversion of stereochemistry. So I'm writing this again to show you how the inversion happened. But I've explained it to you before. Also think of it as a flipping of the umbrella. So when the OH or when the nucleophile attacks from the back side, it just flips the umbrella on the other side and you end up getting the other enantiomer in there. If you have a chiral center. If you don't have a chiral center, it's not a problem, right? Because you don't have any configuration. But only if you have a chiral center, then you're going to get an inversion, okay, in there. So in the cyclic systems, it's a little bit easier to see because here you can see this is cis, right? The hydrogens are on the same side. And then when you add the nucleophile, it's going to come from the less sterically hindered side, so from the hydrogen side, from the back side, and then when it attacks from there, that's where it's going to attach. So now you can see the hydrogens are on the opposite side. So from cis, you end up getting trans, okay, as a product. Okay, so here are some examples, okay, for SN2 reactions. Simple stuff going on here. I have to still go in detail about how you select a substrate, how you select a nucleophile. So these are just examples in there. There's nothing for you to worry about too much except identify the substrate, the leaving group, the nucleophile, okay, all of these things. I want you to kind of understand also that when you see a nucleophile, you may not see it as hydroxide, okay? I may just write NaOH, and if I just write NaOH, you are supposed to know that hydroxide is the nucleophile here. The Na plus, that is just a counter ion, okay? Because you need to have some positive with the negative, right? You can't just have a hydroxide there. It's also called the spectator ion because it's on both sides of the reaction. So whatever the leaving group is now is going to bond with the spectator ion, okay? So you have to be able to recognize those spectator ions in these reactions. And just because I don't give them or I give them, I don't want you to be confused, okay? So if you see just hydroxide also in there, so for example, if I just write, OH minus, then don't think that I'm just putting in a slurry of OH minus or hydroxide. That's not going to happen because there is nothing like just a solution of hydroxide. It's not going to happen, okay? You have to have the counter ion there, okay? So you have to have the salt, all right? So sodium hydroxide, potassium hydroxide, whatever the salt might be. Okay, so I want you to understand that. And then here I gave you an example with a neutral nucleophile. Okay, so where you don't have a salt, so there's no cation here. There's no charge also on the nucleophile. So be careful with that because when you're starting with something like this, where you have nitrogen as the nucleophile, when you attach it to the carbon, the electrophilic carbon, then you're going to end up getting a positive salt. Okay, so the bromide ion now is the counter ion. Okay, it's still there. It leaves, but it is still there because positive needs negative. Okay, so I've written it as plus B or minus, but essentially they're actually together because it's a salt. Okay, just like NaBr would be a salt, then right here this would completely be like one product only. There is no per se as a leaving group, okay? In there is a leaving group, okay? Definitely there is a leaving group, but that's going to be a part of the product now, okay? Because just as a counter ion, not anything else. So just some examples, okay? We'll do definitely more eventually. So what do we use SN2 reactions for? Okay, SN2 reactions are used pretty much for synthesis, okay? Because once you can figure out what kind of a nucleophile you need in order to make a product and you have the right kind of substrate, and you see that I've used X here, X is for halogen. Okay, so fluoride, chloride, bromide, iodide, whatever it is. Some leaving groups are better than others, and we'll talk about that, of course, but right now just have X as a leaving group, and X more than likely is going to be chloride or bromide. In general, fluoride is not used as a leaving group. Fluoride is not a very good leaving group. Similarly, with iodide, we can have issues with that. So your most common leaving group is going to be either chloride or bromide. Okay, if you're thinking about halogens, there are other leaving groups again. Okay, so back to our applications for SN2. So once you know what kind of substrate you have and what kind of product you need, then you decide what leaving group or what nucleophile you want in order to make that product. Okay, so the main thing I want to show you here, okay, with all of these reactions is you can take any substrate, you can take any kind of a nucleophile, and then see how many different kinds of functional groups you can make. So you can make an alkyl halide, a different kind if you want to from what you had, or this may not be a halide. As I said, leaving groups don't have to be halides. So you make an alkyl halide, an alcohol, an ether, a thiol, an amine. Okay, amine. This is not a thioether, this is an amine. So you can make that, or you can make a nitrile, which is a CN. So CN we think of as cyano group, but in organic chemistry we call it nitrile. And then here we can also make an alkyne. So you can see all different functional groups we can make. So which means that as we go through our organic chemistry and we are doing more functional groups, we will be making them using SN2 reactions. So now for the SN1 reaction. The SN1 reaction should go much faster because you know everything about SN2. So I've explained a lot of things in detail to you there. Anyhow, so S stands for substitution. N again is nucleophilic. And then 1, which is superscript again, as I said before, is unimolecular. Unimolecular meaning first order reaction. Okay, so SN1 is a first order reaction. So here is an example of a first order reaction. Here is a substrate, here is the nucleophile. Again, this carbon right here is the electrophilic carbon because it is the one attached to chlorine. So polar bond, that's what you're looking for in substrates, it's polar bonds. And then here's the product, here's the leaving group. You do the same kind of experiment as we did before. You keep one constant and you change the other, right? So here is the a substrate, and the substrate here is kept constant in experiment 1 and 3. You change the concentration of the hydroxide and look, the rate is not changing. So if you change hydroxide, which is the nucleophile, then the rate is not changing. So the nucleophile is not affecting the rate of reaction. How about the substrate? So here you get the hydroxide constant and you double the concentration of the substrate and the rate has changed. Okay, so it means that the rate of reaction is dependent only on the substrate, which means this is the rate, okay, or the rate equation. So rate is equal to K and only the substrate. Now the nucleophile is not involved here, which means that this is a first order reaction because there's only one thing, and that one thing also has only 1 on it, right? Because it's understood, all right, because there's no number on it. So which means it's a first order reaction, which means it's a unimolecular reaction, which means that when we draw transition states, we kind of know that we will have only the substrate involved in it. So once we know we have only the substrate involved in a reaction, now we can proceed to write the mechanism. So here is the mechanism. Okay, so in this case, because the transition state involves only one species, which is the substrate. Now here is the substrate. The leaving group goes away first, creating this intermediate, which is carbocation. So you can see the carbon with the positive, and then the nucleophile will come and then form a bond, okay, with the carbocation. So which means that the first steps that we are doing over here does not even involve the nucleophile in any way. All right, so a few things over here, okay, to note. Just as I said for an SN2 mechanism, here also there are a few things to note. Here you will not see the nucleophile, and here when you see the arrow going, okay, that means that the chloride is leaving with its electrons. Okay, so if it's leaving with the electrons, there is the positive then. Okay, so carbon is left without the electron, so this is a carbocation. We did not have this kind of a species for SN2. Okay, so you have to know the differences between the two. All right, so here is the carbocation. Carbocation is an sp2 kind of a carbon. All right, and sp2 meaning that it is trigonal planar species, which means it is flat. Okay, if it is flat, then the hydroxide can come from either side of the plane. Okay, so it can attack from the bottom, it can attack from the top. Okay, I don't know where the top and the bottom is in 2D. Okay, but you know, keep your hand flat and then you'll understand that's the flat. So which means that the hydroxide can attack from here or from the top. It doesn't really matter. Okay, so if it doesn't matter, that means you're going to get a racemic mixture. Okay, in the product it will be racemic. Now here I did not even give you a chiral center. Okay, what we have here is 3 methyl groups, so it's not even a chiral center, even though I am showing you all the wedges and whatnot, but it is not a chiral center because I just wanted to focus on the mechanism first. Okay, over here. So again, this cross here means it's a transition state. This here means that it's also a transition state. One other thing I want to mention just slightly before I move on from here about the transition state is sometimes you will read this as an intermediate. I think I also said it as an intermediate. So what is the difference between an intermediate and a transition state? Okay, so both of these words we use. Transition state is very fleeting. Fleeting meaning that it just hangs around for microseconds. Intermediate, sometimes they hang around for a little bit more time, which means they're a little bit more stable. Okay, so for example, in SN2, we had typically a transition state, which means that the transition state that the species that we form where the carbon bond was forming and breaking and all that, it doesn't hang around for a long time. Microseconds maybe, okay, that will be there and then it will be gone. We'll have the product in the end. In SN1, usually, you know, we end up getting an intermediate. So carbocations that we end up forming are a little bit more stable. And depending on the nature of carbocation, which again we have to deal with, we have to talk about that a little bit later, they can hang around for a little bit. Okay, so which means that you can isolate them. In an SN2, you cannot isolate the transition state. It's you know, not possible. But in an SN1, sometimes you can. And those are called intermediates then. Okay, so which means they hang around for a little while. Depending on what it is, it might be a little stable. Okay, so just a small difference between intermediate and transition state. And I will, you know, generally for carbocations, I end up saying it's an intermediate. For SN2, I end up saying it's a transition state. Here is the energy diagram for SN1. So SN1, you will have 2 transition states. Okay, so one transition state which is higher in energy is the one that's forming the carbocation, and the second transition state is going to be where the hydroxide is actually attacking. Okay, where the leaving the nucleophile is attacking the carbocation. So you have 2 transition states, you have 2 activation energies. The product can be, you know, exothermic, endothermic, it depends, all right? But otherwise, you have 2 transition states. And then the stereochemistry I already mentioned to you, but here I actually gave you a chiral center. So in this one, you know, once the chloride is gone as a leaving group, so I just write it on the arrow so I don't miss it. You know, I know that I've gotten rid of my leaving group, so minus chloride. And then you end up forming this kind of an intermediate, which is carbocation. So you have empty spaces here, right? Empty orbitals. And so now the nucleophile can attack from either the top or the bottom. And so then whatever you end up getting is going to be a racemic mixture. You will have R also and S as well, okay? Because the attack is happening from both sides, okay? So bond formation is you know, yeah. New bond is forming from either side. So this is something that is different from SN2. In SN2, we only got the inversion. Okay, here you get a racemic mixture. So here are some examples for us for SN1. And in SN1, remember, whenever you are given a tertiary kind of a carbon, then you're going to get an SN1. And so that one here with the nucleophile will give you a racemic mixture. So you have to kind of watch out for that. Okay, this one doesn't have a chiral center, so it doesn't really matter. And the thing about SN1 reactions is that you can have weak nucleophiles also, okay, or neutral nucleophiles which are not that great. You can have those as well because the nucleophile is not part of the reaction mechanism, as in like forming the transition state. Okay, so it's not part of it, so which means you can get away with having, you know, very weak or neutral nucleophiles. Right now, I know this is just the beginning, so at this point, you don't know which one is which reaction. So if you get anything from me, it's going to be that I will ask you, you know, just write me the product if this is an SN1, or write me the product if this is SN2. I will tell you, but in general, eventually you're going to have to be able to predict everything, right? But this is just the beginning, just to give you an idea of what SN1, SN2 is. So for now, this is kind of what you need to know from here. This is not by any means the end of it, okay? I just don't want to make it too big, because you will see the next presentation I have is about dealing with different kinds of substrates and nucleophiles. So don't think this is the end, okay, of SN1, SN2. It's not. This is just the beginning.